So with reheat, the expansion takes place in 2 turbines or more. The first expansion takes place in a high pressure turbine, okay, which is here, to a pre-selected intermediate pressure, and the expanded steam, okay, here, the expanded steam is then passed back to yet another bank of tubes in a boiler where it is reheated at a constant heated at a constant pressure. Okay, so the high pressure turbine is where the initial superheated steam is passed through. Then it's passed then back to a reheater, and it gets it more superheated, and the steam is then expanded in a low pressure turbine here to the condenser pressure. Okay, so Rankine cycle with reheat, and we've already explained the original one with a superheater ends here, but adding a reheat, a reheater here gives you another increase, okay, and another superheater. Then you can replace the original Rankine cycle with a superheater with this, including the effect of the reheat at this stage. Okay, so the new Rankine cycle with reheat cycle is given below, and you can see that there are two work done by the steam. As you can see at this stage, the work is done by the steam or the working fluid between 5 and 6, and also work is done by the working fluid between 7 and 8. Then the two reheaters, the superheater at stage 4 and the reheater at stage 6. Okay, these are accounted for. So in between the heat inlet, there are work done by the steam. Okay, so an ideal Rankine cycle with reheat operates, for example, 4 between 30 bar and 0.04. The steam is superheated to 450 degrees Celsius before entering the turbine, assuming that the first expansion is carried out until the steam is dry saturated. And dry saturated here means that it is not wet. It still has it's still more or less a vapor with very negligible amount of saturated liquid. Okay, so that's why we refer to it as a more or less a high quality steam. Okay, a quality steam, high quality steam, and that the steam is reheated to 450 degrees Celsius. Now, the feed pump term may be neglected, so calculate the heat transferred in and out of the system per unit mass, the work transfer in and out of the system per unit mass, the cycle efficiency, the specific steam consumption, and the work ratio. So we start by drawing out the cycle itself, okay? And we know that the superheater here gets the temperature of the steam to 450 degrees Celsius. Then after the isentropic work done by the steam, leaving the first high pressure turbine, then a reheater gets the temperature of the steam back to 450 degrees Celsius, and it does another work in a low pressure turbine to get it to the compressor operating pressure for condensing. Okay, so this has been illustrated in for the example given the example 4. So we can proceed from there. So assuming that the first turbine is carried out on the steam is dry saturated and that the steam is reheated as we see here. So we can identify the total work in, which is between 1 2, okay, and we know that it's a pump work and it's giving us the change in enthalpy from stage 1 and 2. And the heat added to the system is between two stages. The first stage is between stage 2 to 5, and the second stage is between 6 and 7. Remember the reheater added here. Okay, So, and the summation of that will give you the total, excuse me, will give you the total heat added to the system. Now, the work done by the system, that is the first one between 5 and 6, stage 5 and 6, and the second work done by the working fluid in particular, uh, between 5 and 6 and 7 and 8, and that is given as the change in enthalpies between these two stages uh, for, and the summation of that will give you the work, the total work done by the working fluid. Okay, now the heat lost by the system, or heat lost or heat removed from the system by the condenser is given as the change in enthalpy between stages 8 and 1. Okay, and using the first law as well, we ignore, you know, the reason why we ignore the kinetic and potential energies now by now. So we'll be left with the heat minus the work, the equal to the enthalpy. So going to the steam table, we find the corresponding enthalpies and entropies with respect to the pressure at stage 1. As we know, stage 1 is saturated liquid, so we go to the saturated liquid section of the steam table. We do similar thing for stage 2, but stage 2 is at P30, which is 30 bar, and we need to calculate the work done by the pump here. And as we know, the question asks us to that the pump work is negligible, so we can assume that the pump work is 0. Okay, remember when we calculated the initial pump work, you know, it only gave us minus 3, it only gave us 3 kilojoule per kilogram, right? So 3 is not a large number to be worried about, so meaning that if we neglect that particular, if we neglect the pump work, it wouldn't have any much effect on the calculations anyway. But to be specific, to be more precise, more accurate, you can go ahead and calculate pump work. But if the question asks you to neglect it, there is no point in doing that. Okay, you can actually neglect it. Then it means that the H2 is equal to H1. Okay. So for the stage 3, we know that there is an isothermal heating of heating of the compressed liquid to this stage to get it to a saturated liquid, okay, at 30 bar to the boiler. So we go to the 30 bar section under saturated liquid. We find the corresponding enthalpies and entropy. Okay, so at stage 4, we know that the boiler has already heated the saturated liquid at constant temperature isothermally. That's exactly what it means, at constant temperature, uh, to convert all the saturated liquid to saturated vapor at stage 4. So we go to pressure 30 bar. Under the saturated vapor, we get the values for the enthalpy and entropy. Okay, so at stage 5, we know that it's a superheater attached at stage 4 that uh, produces a high quality steam by increasing the temperature of the steam itself at constant pressure. So we go to superheated section of the superheated steam section of the steam table, and we find the corresponding values when pressure is 30 bar and temperature is 150 degrees Celsius. And when we do so, we will have these values for enthalpies and entropy. So we calculate the at stage 6, between stage 5 and 6, there is a turbine work, uh, which is a work done by the working fluid, in this case steam. So we need to calculate the pressure at this stage, okay, which is P6. So since we don't know the pressure at this stage, then we know the values for the entropy at this stage, okay. So we know that this is a constant pressure heating, so we know the pressure at stage 5, and based on that, we can find the entropy at stage 5. And if the entropy at stage 5 is the same as stage 6, because this is an isentropic process between the isentropic process in the turbine, so the entropy at stage 5 and 6 will be the same. So if we know this information, then we can find with that information we can calculate for the pressure, okay, the change in pressure. So and we arrive at the change in pressure, because if we use the entropy that we found for this stage, and we can use it to track back to find the corresponding pressure on the steam table. Okay, if we do that, we will find that the entropy falls within two numbers. So we need to interpolate for that. Okay, and once we interpolate for that, we can find the value for the pressure which we are looking for, and that value is this. And we have to add that pressure for stage 6 here. Okay, so that stage 6, now we can use it to find the enthalpy at stage 6. So if we go to uh, the pressure at 2.2 bar, because there is no pressure of this in steam table, so we need to interpolate between two pressures that are that this falls within, and we can find the corresponding enthalpy for the corresponding enthalpy for the saturated vapor at stage 6. Okay, so we do the same for the temperature at stage 6 as well. Because we know the pressure at stage 6, we can find the corresponding saturation temperature. So because this is not a standard number in a steam table, so we need to find the ones in steam table to find them, to interpolate for the number that falls between that corresponds to this. So, and if we do interpolation, we arrive at 124.61 degrees Celsius. And with this figure, we've arrived at the pressure, the saturation pressure and temperature of the steam, the low quality steam at this stage 6. Okay, so what do we do? So we take the at stage 7, we calculate for the enthalpy at stage 7. So we know that the stage 7, another superheater or a reheat is attached here to get the temperature of this particular low quality steam back to 450 degrees Celsius. But now the pressure remains constant. Okay, so the pressure at stage 6 is equal to the pressure at stage 7. Okay, and that pressure is given as 2.299933 bar. So if we go to steam table at 450 degrees Celsius, we could not find the value that corresponds to this because the number is not there. So the number falls between 2 bar and 3 bar. Then and the temperature, there is no there is no 450 at that part of the steam table. Then we can do the interpolation, okay, for this. So if we do the interpolation, we arrive at the values, okay, which is this, okay. And if we take the average of the two enthalpies for 2 bar and 3 bar, then we can use that to do the interpolation with respect to this 2.2933 bar, and that will give us the enthalpy at stage 7. Okay, so we do the same for entropy at stage 7, but in this case, we read out the value for entropy and we do the same thing to get the corresponding value for the entropy at stage 7. And now, since we have arrived at the entropy at stage 7, there is another turbine here, a low pressure turbine, and its action is isentropic as well. So meaning that the entropy at stage 7 is the same as the entropy at stage 8. So since we know the entropy at stage 8, we can use that to calculate the quality of the steam which is quality of the steam. You know that low quality steam is leaving this turbine here, low pressure turbine, and the pressure as well will fall to the pressure of the condenser. So meaning that the pressure now is 0.04 bar, and the low quality steam here is a mixture of saturated vapor and saturated liquid. So because it's a mixture, we can find the quality if we know the entropy as is isentropic. Then with that, if we find the quality, then we can calculate for the enthalpy at this point, taking account the gaseous phase or the vapor phase and the liquid phase. Okay, and when we do this, we now know the enthalpy at stage 8 and the entropy at stage 8, which is same as the entropy at stage 7. So with all this information about the enthalpies processed, and we have all of them here, so we can proceed to calculate question A, which is the total heat in and out of the system. So we know that there is heat added to the system between 2 to 5. So we calculate that first, then we calculate the heat added at the reheater at stage 6 to 7. So when we do is the change in enthalpy between 2 to 5 plus the change in enthalpy between 6 to 7. So please, this is a typo, okay? And this is a typo, okay? Please, this is the heat added between stages 2 to 5 and the heat added between stages 6 to 7. And that is equivalent to the enthalpy, the change in enthalpy between stages 2 to 5 plus the change in enthalpy between 6 to 7. So this is a typo, okay? So when we do that, we arrive at these values. When we plug in the values that we know already, and we arrive at this value for the total heat added to the system. Okay, so the heat removed from the system is between 5 to 6 and 7 to 8. That's the no, the heat removed from the system is at the condensation at stage A, so between 8 and 1. So the enthalpy change between 8 and 1 is here. So the work out of the system, which is the work done by the steam and the turbine here, and also the work done by the steam and the turbine at stage 7. So between enthalpy change between 5 and 6 and enthalpy change between 7 and 8. And if we sum it up, it will give us the total work output from the two turbines. So the cycle efficiency now. So we know the formula for the cycle efficiency, which is the net work divided by the total heat in. So we know the net work done by the system, and in this case, we were asked to neglect the work done by the pump. Okay, so because of that, the total net work is equal to the work output from the turbines. Okay, and that is divided by the total heat added between these two stages, and that gives us a 38.7%. So the specific steam consumption, so we know the formula is 3,600 divided by the network, and that gives us a steam consumption of for every kilowatt hour of power generated with the turbine, we consume about 2.4 kilogram of steam. Okay, so as you can see, the steam consumption is reducing the more we add heating in between, the more we increase the quality of the steam and add two turbines. So the work ratio is given as the net work divided by the work output. So since we know that the network, given the negligible work done by the pump here is 0. So we only take the work out is equal to the network, and that gives us unity. Okay, so it is clear that reheating makes only a little difference to the ideal cycle efficiency. Whether reheating increases or decreases the efficiency in comparison with Rankine cycle having the same conditions in the boiler and condenser, this depends upon the point in the expansion at which reheating is carried out. Okay, so meaning that you can add multiple reheat. Okay, so the reheat cycle can be regarded as a combination of Rankine cycle and cycle A, B, C, D, or A prime, B prime, C prime, D. Okay, so if this cycle has a lower efficiency than the Rankine cycle, the efficiency of the combination will be lower also. So the effective average temperature at which the heat is added in the cycle A, B, C, D may well be lower than that of in a Rankine cycle if the intermediate pressure is too low. Okay, so in the regeneration cycle, the basic unsuperheated Rankine cycle includes heat addition under variable temperature conditions between T1 to T5. Okay, so this means its efficiency is less than the Carnot efficiency. If we could instead transfer heat reversibly from the working fluid in another part of the cycle, then all the heat supplied from the external source would be transferred at the upper temperature. So the efficiency would move closer to the Carnot efficiency. So a cycle is a cycle in which this artifice is used to raise the efficiency is called a regenerative cycle. So one potential method which is theoretical possibly is given here. Okay. So as you can see in the diagram, this is the boiler and the turbine with a heat transferred from the turbine, okay, adding heat, okay, kind of so the steam coming out from this turbine is condensed, and the pump is used to perform a work to allow the heat to pass through a series of pipes connected to the turbine, and so that some of the high quality steam or the saturated vapor coming out from the boiler going into the turbine heats up, okay, heats up some of this uh, 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 compressed liquid so that it can get up to the temperature to some temperature required. And with that, you can see that from stage 5 to stage 6, the difference in temperature according to the curve, okay, the boiling curve is not that much, and it can quickly get to the temperature required at stage 6. Uh, uh, and also we can use it to get this temperature closer to the boiler temperature before it is isothermally heated again to saturated vapor at stage 2. Okay, so the feed water at stage C is leaving the pump, okay, could theoretically be passed into passages of the turbine casing at the point where the expanding steam has a greater temperature, only infinitesimally greater than temperature at 6, and the water flows in a direction opposite to that of the expanding steam, and is thereby heated to a temperature only infinitesimally smaller than temperature at stage 2 before it passes into the boiler. Okay, and I've already explained that in the previous slide, and you can see the diagram with the heat exchangers attached to the turbine where this could is used. Okay, so at all points the heat transfer is affected by an infinitesimal temperature difference, and the process is therefore reversible. So most of the expansion in the turbine is no longer an adiabatic process because that is heat. It's used to because of the following, okay, stages 2, 3, and 4. Okay, since the heat rejected in the process 2 to 3 equals the supplied in process 6 to 1, the shaded area underneath the TS diagram, okay, must be equal. So these two areas here. So therefore, the heat supply from the external source is equal to the area under the line 1 and the area under line 2. And the heat rejected to the external sink equals the area under 4 to 5. Okay. So inspection of the areas involved shows that not only are the efficiencies of the regenerative cycle and the Carnot cycle 1, 2, 1, 2, 7, and 8, but the steam consumption also. So on the other hand, the work ratio of the regenerative cycle requiring the negligible pump work between 5 and 6 is very much higher than that of the Carnot cycle and is comparable with that of Rankine cycle. So the regenerative cycle described is impractical. Okay, so first, it would be impossible to design a turbine which would operate efficiently as both turbine and heat exchanger. Okay, mostly turbines are always designed as a isentropic and adiabatic process, meaning that there is no heat added to it. Okay, so secondly, the steam expanding through the turbine would reach an impracticably low dryness fraction. So for this reason, the basic idea of regeneration is applied in a somewhat different way. Instead of the feed water being taken to the turbine, some of the turbine steam is taken to the feed water. So if we do it this way, so the simplest approximation to a practical regenerative cycle is shown in here. So instead of passing from the feed pump to the turbine, okay, through the heat exchanger, then what happens is some of that steam from the first turbine here is passed to the heater, okay, and that is used to add more heat to the liquid uh, at this stage here between stage 6 and 7, okay. So we will have something that looks more like this, okay. So the cycle uh, is stacked on top of each other, okay. So consider 1 kilogram of steam in stage 2 passing from the boiler into the turbine. This steam is expanded to an intermediate stage 3, at which point a quantity Y kilogram is bled off and taken to the feed water heater as shown in the graph there, as shown in the figure there. So the remaining 1 minus Y kilogram is expanded to condenser pressure in the second turbine, okay, and leaves the turbine in stage 4. So in the limit, as the number of the bleedings and feed water heaters is increased to infinity, the mixing process becomes irreversible. All the heat from the external source is supplied at the upper temperature, and the cycle will therefore have the Carnot efficiency. Since a regenerative cycle of this kind is really a combination of cycles undergone by different quantities of fluid, there is some difficulty in portraying it on a TS diagram. Okay, as you can see from the two slides, these are like cycles stacked on top of each other. Okay, so the previous figure must be interpreted as implying that 1 minus y kilogram is carried through cycles 4, 5, 6, 7, 1, 2, 3, 4, 5, while y kilogram follows the path 7, 1, 2, 3, 7. Okay, so so far so far we have been comparing the performance of various cycles on the basis of cycle efficiency and have assumed in effect that combustion process can be carried out with equal efficiency in all parts in all plants. This is not in fact the case. Without discussing combustion efficiency in detail, it can be appreciated that if the combustion gases leave the boiler plant at a higher temperature than atmospheric, some of the latent energy in the fuel is being wasted. Okay, so useful work could still be obtained by operating a cycle between the exhaust gas temperature and atmospheric temperature. With the Carnot cycle, the lowest temperature at which the exhaust gas can leave the plant is the upper temperature of the cycle, which is the critical temperature. Okay, and the Rankine cycle, on the other hand, the exhaust gases could be reduced ideally to the temperature of the water leaving the feed pump. The reduction in the exhaust gas temperature is accomplished in practice by passing the feed water through banks of tubes, heat exchangers, and the economizer situated in the chimney. So these are given in these two diagrams, okay? And these are the banks of tubes here, okay? And the flue gas here for the economizer, okay, passing through this. So the flow is in the direction indicated in the figure so that the hottest gases are transferring heat to the hottest water, and the temperature difference between the fluid is kept to a minimum throughout the process. So one limitation is that the products of the combustion should not normally be cooled before their dew point, otherwise condensation containing corrosive acids may cause serious damage to the economizer tube. So as you can see from the figure, the fan cooling on the stack where the stack of pipes where the flue gas is exhausted. So the dew point of a sulfuric acid vapor is at a higher temperature than that of pure water vapor. And in practice, 150 to 175 degrees Celsius is considered the safer lower limit. So for small commercial and domestic boilers burning natural gas, which is free of sulfur, it is economical to use stainless steel components, and this limit is unnecessary. These are called condensing boilers. Okay, so it would appear that the advantage of higher ideal efficiency possessed by the Carnot cycle is at least partly diminished by its inability to abstract all the energy available in the products of combustion, a further argument in favor of the practical superiority of the Rankine cycle. So the regenerative cycle suffers from the same disadvantages of the Carnot cycle in this respect. So if an economizer is added to the regenerative cycle shown earlier, and the minimum temperature to which combustion gases can be cooled is T1. So when a large number of feed heater is used, the feed water entering the boiler is nearly at boiling point, and an economizer becomes superfluous. So an alternative method of reducing the temperature of the combustion gases, which can be used with all the cycle, is known as air preheating. So the air preheater is a tank of tubes in the chimney through which the combustion air passes through before reaching the grate. The combustion gases are cooled while the temperature of the air is increased prior to combustion. Since the reactants start with a higher temperature, less fuel will be needed to be burnt to arrive at the same temperature of the product. So the net result is an increase in combustion efficiency comparable with that obtained with an economizer. So air preheating is often used in conjunction with an economizer in Rankine and reheat plants, but the degree of preheating cannot be carried as far as the regenerative plant where no economizer is fitted. So one practical consequences of cooling the combustion gas is that only a small amount of the natural draft uh, can be obtained in the chimney. So meaning that some dangerous gases which could be removed from the system are still retained. So the heat exchanging bank tube of tubes, grate and chimney require a fair pressure gradient to maintain the necessary airflow for combustion. So for this reason, a forced draft uh, produced by a fan is always used in modern boiler plant. So the power expended on driving the fan is small compared with the advantage gained by improving the combustion efficiency. So a complete evaluation of an external combustion power cycle must take account of the interdependence between the combustion and the cycle efficiencies, and the adoption of means to improve one efficiency may easily lead to the reduction of the other. So a formal analysis of the plant as a whole is possible using the concept of exergy, which is beyond the scope of this course. So nuclear power plants have been developed mainly on what can be called conventional lines. By using the nuclear reactor as a source of heat for steam cycle, so some effort is being directed towards the direct conversion of nuclear energy into electrical energy via the magneto-hydrodynamic generator, but these efforts still have to be to bear fruit. So we still don't have solutions for this process. So therefore, the next slide shall discuss briefly some of the consequences arising from application of nuclear energy source for steam cycle. So although the principle discussed in the preceding sections apply also to nuclear plant, there is a number of difficulties that are peculiar to nuclear plants. Okay, so they arise largely from present restrictions on the maximum permissible temperature which fuel elements in a reactor are allowed to reach, and from the use of the secondary fluid to transfer energy from them to steam. So there is every prospect that further development of reactor materials will ease these restrictions and therefore remove the least at least some of these peculiar difficulties. As we know that the materials we use in construction of most of our equipment has a tolerance rate. So the materials, the current alloys of metals and the materials we use in building our reactors currently cannot handle the temperatures that will be used that could be generated with nuclear energy. Obviously, we are aware of nuclear runaways that happened in the past, and we can see the devastation of these disasters even till present day. So, and we can also research into so many other ones that are not popularly known. There are so many of them that happened in the past. So that's why the limitations has been put, and there is the current operating ones have a standard temperature that is permitted for the operation, and if they are to exceed that, then they risk accident happening, and we know what happens when that occurs. So the figure shown shows dramatically a simple scheme employing a secondary fluid and circulates through the reactor and transfers heat to the steam boiler. In earlier reactors, the permissible maximum temperature, the Tmax of the secondary fluid leaving the reactor was below the critical temperature of the steam, and it might appear that the cycle shown uh, here gives us the obvious choice. So it's the secondary fluid being here, which we now, with these heat exchangers, the liquid, obviously here will be water, we pass through these heat exchangers, then the secondary fluid passes through here at a T max, which is below the critical temperature of steam, and as it goes through this shell of the heat exchanger, it baits the tube where and therefore transferring the heat to the steam, and the saturated liquid going in here becomes saturated vapor as it goes into uh, the turbine. Okay. So, however, quite apart from the difficulty of excessive moisture in the turbine, which such a choice would entail, it should be remembered that the secondary fluid falls in temperature as it flows through the heat exchanger, and therefore the saturation temperature at the steam must be well below T max. So this is most easily appreciated on the temperature enthalpy diagram shown next, and where H is the product of the mass flow and the specific enthalpy of the respective fluid. So as we can see here, so the new temperature enthalpy diagram shows us the pinch point and where the secondary fluid, okay, the pinch, I don't know if you have done heat integration. The pinch point is a point where the temperature here uh, determines how the heat exchanger will operate. It gives you the maximum temperature at which there will be deviation, a standard, a particular point that shows you the temperature difference that you need to have within the system that the two fluid cannot go beyond. So meaning that this is it could be a difference of 10 degrees Celsius, 20 degrees Celsius, so depending on the fluid and the steam, and obviously the material here, which is water, then the pinch point here gives you that particular temperature difference that they cannot go beyond. Okay, so and we can also redraw this on a different to highlight the temperature marks for the boiling fluid, the mass flow, and the low mass flow. Okay. So the change in enthalpy must be the same for the two curves, it it being equal to the total quantity of heat transferred. The saturation temperature is chosen so that at the so-called pinch point, the secondary fluid temperature is marginally higher than the saturation temperature. So it can be seen that under this condition, at certain amount of superheating is possible. So the secondary fluid temperature drop for a specified heat transfer can be varied by varying the mass flow as indicated in the previous figure B. Okay. So at a higher mass flow, it enables a higher saturation temperature to be used for the power cycle, and thus a higher steam cycle efficiency to be obtained. But it also entails a higher circulating power, pump power, and it is the net turbine power, is the net turbine pump work, which is important. So uh, in this kind of system, we will need a higher circulating pump power. Okay, and the pump, as we know, does the work to get the liquid up to the boiling pressure, and the turbine itself, the steam itself, does the work. So we need a net work done by these two systems to determine what to do with the system in terms of the efficiency. Okay, so it is obvious that the steam condition cannot be optimized on the basis of steam cycle efficiency alone, but must be considered in conjunction with the pumping power of the secondary fluid cycle. Okay, we need to acknowledge the network done by the done within the system, okay, as well, not just the cycle efficiency. So a higher mass flow, uh, as we know, enables a higher saturation temperature to be used for the power cycle, and thus a higher steam cycle efficiency to be obtained. And with the net, by knowing the net work done within the system, then it will be obvious that the steam conditions cannot be optimized on the basis of the steam cycle efficiency alone, but considering the pumping power and the secondary fluid. Okay, and this will be the end of this lecture. And at this stage, with further studies, you should be able to calculate all the questions presented in the tutorial. Okay, and most of these questions will obviously focus on the Carnot cycle, the Rankine cycles, including the superheated one and the reheat. Okay, and I will see you guys in the tutorials, and bye for now.